Hello everybody, my name's Simon Whiteley. Welcome to this live webinar with myself and Professor Nancy Leveson. Just to go through a little bit of housekeeping on the webinar. Obviously this is the first one that I've ran, so it's not likely to be smooth, and apologies for that, but we'll do the best that we can. So today's agenda, we're going to do, as I said, do a little bit of a webinar introduction, 5 to 10 minutes, just to introduce myself and my very special guest, Professor Nancy Leveson. Do a little bit of webinar housekeeping so that everybody's comfortable with how the software works, and if they need to ask questions, they can. Then we'll go through and do Nancy's presentation, which will be about 45 minutes, maybe a little bit longer, and then we'll do the Q&A at the end. If you do have any questions during the presentation, you're most welcome to ask them in the questions box, but it's, due to the nature of the way we've set this up, it will be towards the end of the presentation that we address those. But if you do have anything else, please don't hesitate to raise your hand and I'll see what I can do. Okay, so the people. So there's me, my ugly mug. My name's Simon Whiteley, if you don't know me. I'm an independent system safety engineering consultant and director of my own company, Whiteley Aerospace. I've worked across system safety across all parts of the engineering life cycle and also the product life cycle, and across a number of industries, predominantly civil and defence aerospace, including air traffic control, but also defence land, maritime and defence nuclear. I'm an active member of a number of special interest groups focused on developing and promoting system safety and STAMP in general, but also more specifically in pharmaceuticals and healthcare, including the application of STAMP to drug development and clinical trials. Professor Leveson, she's been a professor of aeronautics and astronautics at MIT since 1999. Before that time, she was at the University of Washington and the University of California. In 2000, she was elected to the National Academy of Engineering, and Professor Leveson conducts research on system safety, software safety, software and system engineering, and human-computer interaction. She served on the panel that investigated the 2005 Texas City refinery explosion and also assisted with the official reports on the 2003 Space Shuttle Columbia loss and the 2010 Deepwater Horizon drilling rig accident. Dr. Leveson has published more than 200 research papers and is an author of 2 books, Safeware, System Safety and Computers, published by Addison Wesley in 1995, and also Engineering a Safer World, which I'm sure you're all now very familiar with. She also consults extensively with industry on accident investigation, prevention and analysis. Okay, so webinar housekeeping, go to webinar. I've already said in the email, but just be aware, today's webinar is being recorded and will be made available as soon as possible after the webinar. Hopefully this is the type of screen that you should see if you're using a PC or a Mac. You'll see on the right hand side, this is the control panel. On the left hand side here, this is just highlighting the various controls. So this little red arrow on the left hand side here, that should collapse and expand the control panel so you know what you're doing. And then you've got the questions box. And this is the same questions box that we'll use towards the end of the webinar to address various questions that you might have. If you do want any support or you want further information, please email me at that email address. And oh yeah, of course. So I just want to say thanks to all of you that filled out the registration survey and providing feedback and questions for us to consider. That feedback has enriched the presentation that we're about to provide, and it will also enrich some of the questions that you provide. So just to give you a sort of understanding of who's on this webinar with you. So we've got people from over 25 countries across the globe. So we've got people all the way from the west coast of America and Canada right around the globe to the other side in Australia. And I'm sure they're struggling because it's 1 a.m. over there. We've got over 175 people and that covering 15 plus industries and domains, including the ones that you can see there. So this is, just highlights to you how sort of broad the interest is in STAMP and systems thinking. Okay, so now to get to Professor Leveson's introduction. So I'll hand over now to Nancy.
Can you see, Simon?
Yep, we can see your slides. Ready to go?
Great. Hello, everyone. Welcome. Good morning or good evening, depending on where you are. I'm going to talk about a new approach to safety and cybersecurity today. There were some people who wanted worked examples. I'm afraid I'm not going to have the time to go through a lot of examples or really do real full examples. But I'll tell you at the end where you can find them. There are lots of them available, and if there's enough interest, we'll do future webinars on how to actually training on how to use the tools. But today, my goal is to answer the following questions. First of all, why do we need something new? We've got tools available now. Why is there a need for something else? What is STAMP? How does it differ from what people do now? What kinds of tools are available for STAMP? How it's being used, and finally evaluations. Does it really work? And there's been lots of evaluations, and you'll see lots of evidence now understanding the comparisons between it and all of the traditional methods and most of the standards that are being used today. So let's start out with why do we need something new? Well, I'll start with where I started and how I ever got into this, because my degree, my PhD was in computer science, and before then I worked for IBM as a system engineer and a software engineer. But I got my degree in 1980, and I got my first teaching position and got a call within the first week from somebody making a torpedo. It's called ADCAP. Again, this is 1980, and they were really concerned because they had more software on this torpedo than they'd had in the past. Now, that wasn't a whole lot compared to what we do now. What we do now, this old ADCAP system looks pretty simple. But at that time, they were sort of flummoxed about and didn't really understand how in the world they were going to fit this into the standard approach to safety engineering. And so I worked with them, and I learned. I think I didn't help them a whole lot, but what I did was learn system safety engineering from old school system safety defense engineers, and I learned a tremendous amount, and started working on this. Thought I'd spend maybe a year solving the problem, and it's 36 years later, and I finally think I may have solved the problem. So what is the problem? Well, the basic problem is that our current tools are all 40 to 65 years old, but our technology is very different today. If you look at on the left on that timeline, you see that FMIS is probably perhaps the oldest. It was for electronic systems after World War II. And then in the 60s, there was a spate of new tools, fault tree analysis, HAZOP, event tree analysis, bowtie, which is just a combination of fault trees and event trees. And all of these assume that accidents are caused by component failures. And that was true for most of those systems, and we'll talk a little more about it. In the late 70s, all of a sudden, people started using computers in control, which resulted in exponential increases in complexity, lots of new technology, new ways of doing things, and changes in the way humans work in systems. So for most of us at the very beginning, and probably a lot of people still, the idea was they thought that they would take these old techniques and just extend them to computers and into the new roles of humans and systems. And I worked on that for a long time myself. Around the year 2000, I really sort of gave up and said, this isn't working. We aren't getting anywhere. And the basic problem is that all of these old techniques are based on a different model of how accidents occur. But with these changes, accidents and the causes of accidents have changed. So really the culprit here has been software, although it's not just software that's the problem, but it's causing destructive problems. It's allowing us, for example, to increase the complexity of our systems. And the first thing is that all the old techniques are based on failure, but defined in the engineering terminology of failure. Software doesn't fail. It's simply the design of a machine abstracted from its physical realization. Now, this is why it's been so incredibly revolutionary and has totally changed engineering. We don't make anything today without software in it. But it's pure design. Designs don't fail in that sense. Now, people misuse the word failure, and you can use your word any way you want, but the problem is the old techniques don't use it in the way that software misbehaves. So it's only a random failure, so it'll never happen again. Software doesn't have random failures like the old techniques, the old hardware components do. The second is that the role, and this is really important, the role of software in accidents almost always involves flawed requirements. Every single accident, I've seen hundreds of them involving software in the last 36 years, and every single one I saw, I could trace back to the requirements. It wasn't a coding error. The requirements were either incomplete or had wrong assumptions about the controlled system or about the required operation of the computer and the software, or it had unhandled control system states and environmental conditions. So we spend a lot of our time, and most of the standards even for safety focus on the autopilot provides requirements to the software engineer. The software engineer then takes those requirements and is actually doing the design of the autopilot, the design of the system. And we focus on this implementation of the requirements mostly. But the problem is that's not where the safety problems are rising. The safety problems are arising in the development of the requirements. So only trying to get the software correct or make it reliable isn't going to make it safer under these conditions. The third impact and the problem that's occurring is that software allows almost unlimited system complexity. We can no longer plan, understand, anticipate, guard against all undesired system state behavior. When we were building relatively simple electromechanical systems, we could get most of the system design errors out before we used the thing. And we could exhaustively test to get those out, or we could just think through the problem pretty carefully. And what that meant was that we were able to worry only at runtime about failures of components, because we knew components would break and fail randomly. That happens in hardware. So we didn't have to worry about anything else. That's no longer true. Now we have these design errors that are getting through to operations. And a second important concept is that the context determines whether the software is safe. The Ariane 4 software, the inertial reference system, was safe in the Ariane 4. That software was perfectly fine. When it was reused in the Ariane 5, the spacecraft exploded. The software didn't change. The reliability didn't change. There weren't new coding errors that were introduced. The problem is that safety is not a component property, and I'll talk about that in more later. It's a system property. So when we talk about the SIL concept, this is going to probably upset some of you, but the safety integrity level concept is technically meaningless. You can talk about the reliability of a component, but you can't talk about the safety of a component unless you know exactly what context that component is going to be used in. And in fact, reused software is one of the major causes of accidents in spacecraft software. So it's not possible to look only at the software and determine whether it's safe. You have to know what a system design the software is operating in. So here's some examples. I have a couple examples of accidents with no component failure. This was a real accident. I have the details are all secret, but this is open. Some Navy aircraft were ferrying missiles from one location to another, and they put the missiles on the wings of the aircraft, and they were moving them. So, flying them from one place to another. One pilot executed a planned test. They've been told to do this by aiming at the aircraft in front of him and firing a demo missile. I guess they figured that why waste his time while he was sitting there? He might as well do something useful. Unfortunately, no one involved knew that this was so-called smart software, and that the software was designed to substitute a different missile if the one that was commanded to be fired was not in a good position. In this case, there was an antenna between the dummy missile and the target, so the software decided to fire a live missile located in a different, better position instead. So if you look at this, nothing failed. The human did the right thing. He didn't do something wrong. The software didn't do anything wrong. The aircraft didn't do anything wrong. The problem was in the interactions between the components and a lack of understanding by the system designers and the system operators of how each of the components was going to work. Here's another example. This is the Mars Polar Lander. That was the one that crashed into the surface of Mars. And you have to slow down the spacecraft to land safely. It comes in very fast. They use the Martian atmosphere, parachute, descent engines, which are the latter are controlled by software. The parachute, there's a parachute in this specific mission. They had a parachute they deployed behind the spacecraft, which would slow it up. The descent engines were engines that were acting in reverse against the direction that the spacecraft was moving. Now, the software has to know that the spacecraft has landed, because if it doesn't, then what'll happen, they'll land, and then the descent engines are still going on, and so it's going to push it up and it'll hop and destroy itself. So they put these very sensitive sensors called Hall effect sensors on the landing legs, and the software engineers were told that when they get input from those sensors to cut off the engines immediately because the spacecraft has landed. Now, it turned out that when the parachute is generated, there's some noise or false signal. There's a jerk on the spacecraft, and the sensors send out some signals. That wasn't in the software requirements. They were never told about that. It may have been the engineers all knew about it, the hardware engineers. Probably they didn't think the software wasn't supposed to be operating at that time, so maybe they didn't think they had to tell them. But the software engineers decided to start the software early to even out the load on the processor, so when it got that noise from the sensors, it thought the spacecraft had landed and shut down the descent engines. Now, if you look at that, nothing really failed here again. The system engineering didn't work, but I don't know how I dislike the use of the word failure for engineering efforts. There were mistakes made. They didn't really understand all the implications of the interactions between the components. So there are two types of accidents. The ones we used to have to deal with, and that are techniques, old hazard analysis techniques work very well on a component failure accidents. Accidents caused by single or multiple component failures, we usually assume some kind of randomness in those failures. And we still have those, although we're getting much better at building very reliable systems and using sophisticated redundancy, so we've cut those down. But more important now are these component interaction accidents that arise in the interactions of the components. They're related to complexity. They're exacerbated by the introductions of computers and software, but the problem is system design errors. The problem is not software design errors. There could be software requirements errors, but not software design or coding errors. The other thing that software has done is change the role of humans in systems. The typical assumption that is that operator errors that cause the most incidents and accidents. So what should you do? Well, do something about the operator. Fire them, admonish them. Often we say, well, we'll just train them not to make those mistakes. Or we do something about operators in general. We can marginalize them by putting in more automation, so now they're farther away from the system and have more difficulty overseeing and monitoring the automation. Or rigidify their work by creating more rules and procedures which they probably won't be able to follow. A systems view of operator error and a more recent operator's view is very different. In this view, operator errors isn't the cause of an accident. It's a symptom. It's never a cause. All behavior, human behavior, is affected by the context or system in which it occurs. And because we're changing the role of operators in software-intensive systems, so are the errors that they're making. We're also designing systems in which operator error is inevitable, and then we blame the accidents on the operators rather than the designers. We've got to have ways of not doing this anymore, or we're just not going to make much progress. To do something about operator error, then we have to look at the system in which people work, the design of the equipment, the usefulness of the procedures, goal conflicts, production pressures. The bottom line in this view of system safety and systems view is that human error is a symptom of a system that needs to be redesigned. And we'll come back to that a little bit more. So that's why we need something new. So what's STAMP and how does it differ from what people do now? And the problem really is complexity, and the complexity of the systems we're building today. If we were building simpler systems, we really wouldn't have these problems even if we had software in them. And there are three different ways that you can cope with complexity: analytic reduction, statistics, and systems theory and systems engineering. So let's start with analytic reduction. This goes way back to Descartes and the modern science. And what they said was, well, if you have a complex system, what you do is you divide it into parts, distinct parts for analysis. So for the physical aspects, we separate the physical or the functional components. And if we're interested in behavior, then we look at events over time. And then we examine each part separately and later combine the analysis results. So for physical systems, you can do some analysis on each component. Maybe if you're interested in reliability, you can find the reliability of each of the components and later combine it all to get the results for the system. But the problem is that this assumes that such separation doesn't distort the phenomenon. Of course, there's lots of systems, a very large number for which this is true, but it's not necessarily true anymore, these assumptions for the systems we're building today. These assumptions include things like each component or subsystem operates independently, that the components act the same when they're examined singly as when they're playing their part in the whole, and that the events aren't subject to feedback loops and nonlinear actions. these, as I said, in our complex systems we're building today are no longer true. But the traditional approach to safety is built on this, and that's surprising. That's the way we deal with most engineered, and have in the past dealt with most engineered systems. And it's reductionist. What they do is you divide the system in components. You assume that the accidents are caused by component failure. You identify chains of directly related physical or logical as functional component failures that can lead to the loss, and then you evaluate the reliability of the components separately and later combine the analysis results into a system reliability value. And you've all seen this in FMIS and fault trees if you've done safety analysis before. But note that there are some assumptions here. We assume randomness in the failure events so that we can derive probabilities for a loss. But software and humans don't satisfy this assumption. And humans especially in what they're doing today. Humans used to just follow a bunch of procedures, and maybe there is some kind of randomness on whether the human hit the right button or not according to the procedure they were following. But that's not what they're doing anymore in systems. That kind of behavior has all been automated. It's all done by software now. The humans are overseeing and monitoring and making decision making, and this is not random. So this accidents as chains of failure events forms the basis for just about all the techniques we do today, and it also forms the basis on design. So we concentrate on dealing with component failure, redundancy and barriers, prevent failure propagation, high component integrity, over design, build it stronger than it needs to so it won't break, fail-safe design. In software, do a whole bunch of formal verification that or testing or whatever to ensure that the software actually implements the stated requirements. And for humans, we use all operational procedures, checklists, training, and so on. The problem is that safety and reliability, while they were close enough in the old approach to be substituted for each other, they're no longer true. They're very different today. So if you look at the green circle shows the scenarios involving failures. The pink circle represents unsafe scenarios. Now in the green, non-overlapped green part in section A, what we have are with systems that are maybe unreliable, but not unsafe. And FMIS handles those well. In the overlapped C part of the two circles, we have unreliable and unsafe systems. And FMIS, FTA, HAZOP, event tree analysis, all of those things that were developed long ago work for those. The problem is in section B, which are unsafe but not unreliable. There's been no failure. And it's those scenarios that are not handled in what we're doing today. So preventing component or functional failures isn't enough. This is one of my favorite cartoons. It's still hungry and I've been stuffing worms into it all day. Everybody means well. Everybody's trying to do the right thing. The problem is they're like the little birds. They're solving the problem they're used to have solved, but not the new problem. And so we're stuffing worms into the baby, and the baby is getting some nutrition, I guess, but we're not really solving the problem we need to solve. So we need something new. All of these things I've talked about don't fit into reliability-oriented approaches to safety. And trying to shoehorn new technology and new levels of complexity into the old methods just isn't working. People have been trying it. Oh, they talk about doing software fault failure modes and effects analysis and software fault trees and all that. Most of the stuff, everyone I've ever seen is nonsense. It doesn't work. It isn't it isn't realistic with the way the software, humans, and new complex systems work and have accidents. So what's the alternative? Well, the alternative is to base this on systems theory. Systems theory was developed for systems that are too complex for complete analysis, where when you separate it into interacting subsystems, it distorts the results. The most important properties in this system are emergent. I'll get back to that because that's really critical. But what that means is that they emerge when you put the components together. They aren't necessarily in the individual components. So if you talk about the cells of an apple, you can't see the shape of the apple in the individual cells. It's only when you put them together that you get a concept of shape. Systems theory also was developed for systems that are too organized for statistics. There's too much underlying structure that distorts the statistics. And in addition, new technology and designs just don't have historical information, so there's no really way to get that. Systems theory is not new. It's actually pretty old. It was first used, it was developed in the 40s and 50s by some mathematicians and by biologists, because humans and organic systems don't do well, aren't well represented by analytic reduction. It was first used on the ICBM systems, the intercontinental ballistic missile systems of the 1950s and 60s, because they were having lots of accidents, and they were related to this. They were component interaction accidents. The first time we really started seeing that and realized they needed something new, that component reliability, just making every component reliable, wasn't going to solve their problems. And it's the basis, really, systems theory for system engineering and system safety. Now, there's some people say they're doing system engineering, but they do analytic reduction, and they say, well, I'm working on a system. Well, that's not exactly the way system engineering was originally defined. So what is systems theory? I'm not going to go into the math. We don't have to go into the technical part. It focuses on, but you're going to, for those of you who worked in system engineering, which is probably most of you on the call, on the webinar, this is all going to sound very familiar because it's the basis for system engineering. And systems theory focuses on the systems taken as a whole, not on the parts taken separately. And there, as I said, these emergent properties. These are properties that can only be treated adequately in their entirety of the system, taking into account all the social and technical aspects. You've probably all heard the whole is greater than the sum of the parts. That's really the essence of emergent properties, that and of systems theory. And these properties, these emergent properties, arise from the relationships among the parts of the system, how they interact and fit together. So let me show you this diagrammatically. So here are some components. Here's a process, and with some individual components, and they interact in direct and indirect ways. And in their interaction, these emergent properties arise from complex interactions between these. Safety and security are both emergent properties. If I show you a valve and I say, I'm going to use this valve in my car, will the car be safe? Well, I don't know. I can tell you whether that valve is reliable, whether it satisfies its requirement specification, but I can't, because reliability is a component property, but safety is not. I can't tell you. It depends on what we're doing with that valve and how it interacts with the other components in the car. So what do you do for emergent properties? Well, to control them, you need some kind of controller that enforces constraints, safety constraints, or constraints on the behavior of the system by controlling individual component behavior and also controlling component interactions. And this controller provides control actions on the process and gets feedback. Now, for those of you who have had any basic engineering course, what you see is a basic feedback control loop. And yes, that's exactly it. And much of modern control theory really stems from these ideas that were back in the 40s and 50s. So I said that the controllers enforce safety constraints. What are safety constraints? Well, here's some examples. Power must never be on when the access door is open. So we have we have to enforce the interaction between opening the door and the power supply. 2 aircraft automobiles must not violate minimum separation. Aircraft must maintain sufficient lift to remain airborne. The integrity of a hull must be maintained on a submarine. Toxic chemicals or radiation must not be released from the plant. These are really the high-level functional requirements, the what and why, that we need to address during design, the how. So here's an example of a control structure. This is ACC stands for Adaptive Cruise Control. BCM is the brake control module. We have an operator controls some instruments. It gets feedback from them, usually visual, maybe oral. And the instruments are controlling, the cluster is controlling the adaptive cruise control module. It gets input from radar about the lead vehicle, the vehicle in front. It also sends signals to the braking control module when it appears that we need to brake. The brake control module sends a braking signal to the brake. The brake, through friction, stops the vehicle. There's feedback, usually of various kinds. You can do it, for example, by the speed of the wheels gives feedback to the brake control and to the eventually to the ACC, which provides feedback to the ACC module. There's ACC is also controlling the powertrain, the electronic throttle body, and so on. The operator may have an acceleration pedal, which also provides feedback in here. So this control structure, and this is just a control structure, implements adaptive cruise control for on an automobile. Now, what we're going to do, just to give you a hint, is we're going to actually do the analysis on this, not on a physical relationship, physical diagram of the system, but on this functional diagram of the system. And the hazard analysis, the analysis techniques that we use are going to actually work on this kind of structure. Now, this is just focusing on the physical process. In front of you, you can see and the red is the operating process. The physical process is just on the very bottom right of this diagram. It may be controlled by some automated controllers, which are controlled by some human controllers, but we have a whole social and managerial organization above that control structure, and on the right we have operations. On the system, on the left we have system development. So in operations, above this operating process, we have operations management, which provides work instructions, again, gets various kinds of feedback. Company management provides standards, policy. Government regulatory agencies, user associations, industry associations, unions, insurance companies, courts, and all of these things. I just drew them all to make this simpler in one area here, but they're providing all kinds of things to controls on the system and on controls on the management, for example, regulation, standards, certification, legal penalties, and they get, again, feedback. And we may have Congress and legislatures involved if in some cases. On the left, you have system development. Again, it may start with Congress and legislatures. We have all of these quasi-governmental or user associations. We have company management, project management, design implementation. Over on the bottom left, we have manufacturing. There's a lot, maintenance and evolution. In the middle is interactions. There's lots of other interactions which I didn't draw in here just to make it less complex. But what this means is because we're doing the hazard analysis on this control structure, we can include not only the human controllers and the software, the automated controllers, but we can include management, we can include government, we can include, somebody asked the question, can you do government disaster management by local communities? Absolutely, that's being done right now. We can look at actual development of the systems on the left. And we can include this in the hazard analysis because they obviously impact whether we have accidents or not. So there's one other small thing we have to do. The role of process models, one more technical thing, and then we can get off to the tools. In any controller, there's a control algorithm. If it's an automated controller. If it's a human controller, it's not really an algorithm. They sort of generate decisions in various ways. But both of them, any controller has to have a model of the process that it's controlling, called the process model. Otherwise, it can't provide adequate control instructions without having some understanding of how this control process works. So the controller uses the algorithm, it uses its current model of the state of the process to generate control actions. The control process feedback, there's feedback usually generated to help update the process model to what the state of the process currently is. Now, accidents often occur, especially accidents that are related to software and to humans, operators, because this process model is incorrect. So remember the Mars Polar Lander. The software thought that the spacecraft, which was a controlled process, was on the surface of the planet. Why did it think that? Well, it got some feedback that it should have handled or shouldn't have gotten, depending on the system, what system design you wanted to substitute. But it got feedback that the control process that the spacecraft had landed. So it thought the spacecraft had landed and generated a control action to turn off the descent engines. The software didn't fail in any way. It did exactly what it was supposed to do or intended to do by the engineers. Now, there was a system engineering error, and the system engineering wasn't correct. But the controller itself didn't fail in any way whatsoever. And this is a much better model of how humans and software interact in or influence accidents than the old failure model. So there are 4 types of unsafe control actions, and you can think of that. These are the only 4 that could happen. Control commands required for safety aren't given. So let's think about air traffic control. 2 aircraft are flying at each other, and the air traffic controller needs to send a command for at least one or both of them to change their trajectory, but they don't. That's that first case. There could be unsafe ones that are given. The 2 aircraft aren't on a collision course, but the air traffic controller puts them on one by giving unsafe commands. Potentially safe commands are given too early or too late, or control stops too soon or is applied too long. This is for continuous control actions. So for example, if you tell the pilot, the air traffic controller tells the pilot to go up to 30,000 feet, and instead he or she levels off at 25,000 feet. So those are the 4 types of unsafe control actions, and we're going to use that along with our control structure to create a brand new type of hazard analysis that's more powerful than the ones we have, the old ones from 50 years ago. So what is STAMP? And this is going to be very quick. This is just that STAMPs defines, it's a new model of how accidents occur, because the old model saying accidents occur because of chains of component failures is no longer relevant in most of our systems today. So it defines safety as a control problem versus as a failure problem. It applies to very complex systems. I'm going to show you. We have tried this, and this has been tried on the most complex systems built today, anywhere in the world. And it has worked like a charm. And I'll talk about it later when we talk about evaluation. It includes software, humans, operations, management, government, regulation. It includes all of these things, whereas the other techniques really don't, or if they do, they treat them superficially. They say, put a box in a software and say, in fault tree, and say software fails. Well, I don't know what that means. Human failed. Unless their heart stopped, I'm not sure that that's a very good description, and it isn't useful. It doesn't provide us with the information we have to make safer, build safe, and design safer systems. STAMP is based on this general systems theory and systems engineering, and because it's based on that, it fits really well right within the system engineering that all your companies, most of you are doing. It fits perfectly in a model-based system engineering world. It expands this traditional model of accident causation. It's not just a chain of directly related failure events, but losses are more complex processes. So hazards result from the lack of enforcement of safety constraints in system design and operations, not just from component failures. The goal then is to control the behavior of the components and the systems as a whole to ensure that the safety constraints are enforced in the operating system. Now, what this is just a change in emphasis. We aren't eliminating anything the people did before. We're adding to what we used to do. So instead of just looking at preventing failures, we enforce safety and security constraints on the system behavior. Note that by enforcing constraints, that might require preventing failures. We're not saying, or handling them. We're not saying that failures can't cause accidents. We're saying that there's more than that today that's causing accidents, and we need to include more than just enforcing, preventing failures. Okay, so what kinds of tools are available? STAMP is just a theoretical causality model. It isn't a tool itself. It's not a methodology. It's a model of how we think about accidents are caused. But we can build a lot of tools on them, and we have, and then we can take those tools and put them together into processes. So we have an accident analysis tool that's been developed called CAST. By the way, other people could be developing these tools. It doesn't necessarily have to be limited to my group. We have a new hazard analysis technique called STPA. This is brand new, a PhD dissertation, STECA. The PhD dissertation was last January, so it's been about a year. It's called Early Concept Analysis, and what it basically does is apply hazard analysis during the early concept analysis phase before you have any design. And then we can use these tools then to develop design, to design safety and security into a product before we actually build the thing. We have a model-based system engineering tool, Spectrum. We can do organizational cultural risk analysis. We can identify leading indicators of risk, and we have this new security analysis technique. This was actually cybersecurity. This was actually a dissertation only the final defense was in November or December. It's really, really new, and you'll see it's taken the world by storm. It's been used all over the place. I've never had a dissertation that was used so quickly before it was ever finished. And we can put these tools together into system engineering processes, risk management processes, operational safety, management principles, organizational design, regulation, and so on. So now I'm just going to go very quickly through a few of the tools, and I'll show you partial example of STPA. I'm not going to have time to do the others because I don't have enough time here. As I said, at the end I'll show you where there are worked examples and we can get a lot more information. STPA is a top-down system engineering analysis technique. It identifies the safety constraints, the system and component requirements. And you'll see I have an example. I'll show you how we identify the software safety requirements using analysis. And we actually have tools that can do this. I have an automated tools to do this. Why I mean X is this works on any emergent property. So it works on security, but it works on quality, it works on producibility, it works on anything that's an emergent property, and we're starting to look more at that now. It identifies the scenarios leading to the violation of the constraints, the requirements, and then we can use those results to design or redesign the system to be safer. So we can do two things. We can generate the requirements, and we can look at how those requirements might be violated so we can design the system to be safer. It can be used on technical design, organizational design, human factors, humans. It supports a safety-driven design process where the analysis influences and shapes the early design decisions, and it's iterated and refined as the design evolves. And as I said, it's easily integrated into system engineering and model-based system engineering tools because we've been able to do that. So here's a quick example. This is another accident with no component failure. This is a real accident, happened in the UK a while ago. This was a batch chemical reactor. The computer opened and closed the valve here that allowed catalyst to go into the reactor and start the reaction. It also opened and closed a valve that allowed cooling water to go into a reflux condenser, which cooled off the reaction to make sure that it didn't overreact and explode. And the computer also had some inputs from various parts of the plant that it was monitoring. And the software engineers were told, if you get an input from any of these inputs, it means something's gone wrong. What you should do is stop everything, sound an alarm, and call the operators. So that's what happened. One day they got a message that there was a low oil level in a gearbox. The computer stopped everything. The operators went and put more oil in the gearbox. But this happened after the computer had opened the catalyst valve, but before it had opened the water valve. So so it stopped and therefore never finished opening the water valve. While the operators were over at the gearbox fixing things, the reactor overheated and noxious stuff was vented out into the neighborhood for people to breathe. And if you look carefully at this, again, every component satisfied its requirements. It did what it was supposed to do. The problem was in the system engineering and in the software requirements. One solution, there's multiple solutions on any of these problems when you have interaction accidents, but one solution would been to tell the computer software engineers, always open the cooling water valve before you open the catalyst valve. But nobody thought of that. The engineers may have thought it was pretty obvious, actually. They've told me that, well, of course, every chemical engineer knows that. And I say, well, these software engineers weren't chemical engineers. This is the classic, it's a fairly simple system, easy to describe, but it's the classic kind of problem we're having with software and accidents. So we start by generating a functional control model. The operator controls the computer, which controls the valves, and we have some control actions: start process, stop process, open and close the water valve, open and close the catalyst valve for the computer. Excuse me, we have some feedback. We may not know what the feedback is here, but during the analysis, we'll find out what it has to be. Now, I want you to first look and see the difference between the physical model and the functional control model. They don't look at all like each other. We usually build physical models for the software people on the line. That's the architecture. That's the physical connections between things. We don't usually build the functional control model, but that's what we really need to understand how this thing operates and to do safety analysis. So I told you there were those 4 causes. So let's say the hazard here is catalyst in the reactor without the reflux condenser operating. That is water flowing through the reflux condenser. So here are on the left column, there are the 4 control actions of the software. Just going to look at the software for this time being. We can look at the human, and we would normally. Humans are are treated just as other components in the system. They aren't treated any differently than any other hardware or software component. Your control actions: open water, open catalyst, close the catalyst valve. And across the top, we have those 4 types. If you remember, those 4 types of unsafe control actions, and we fill in here this thing with the conditions under which this control action will be unsafe. So not providing the open water command when the catalyst is open is unsafe. Closing the water valve while the catalyst is open is also unsafe. Now, I'm not going to tell you how to generate. Again, we could do this, but there's lots written about this, and I just don't have time. But if you look at what we can get out of this, are some high-level requirements on this system. The water valve must also always be fully open before the catalyst valve is open. If we want to look at timing, water valve must never be open. The complete opening more than X seconds after the catalyst valve opens, and the catalyst valve must also never be closed more than X seconds after the water valve. So what we've generated here are those missing requirements, the safety requirements on the system and on the components of the system. The next step is to identify the scenarios that lead to the violation of the safety requirements and either eliminate or mitigate them. So, for example, let's look at the cause of the hazardous control action. We open the catalyst valve when the water valve isn't open. Now you can start by considering how could the process controller's process model identify that the water valve is open when it's not, because the only way that someone would issue without being malicious would open the catalyst valve is that they think that the water valve is open. How could that happen? Well, here are a few reasons. The software, for example, previously issued an open water valve command, but the valve didn't open. It was jammed, it failed, or something. But it assumed that the command had been open. Why would it assume that? Well, there may be no feedback. So what's the control? Well, you put feedback into the design, or the feedback wasn't received. Now, we could go on with more analysis to determine why it wasn't received, or if there's a solution, an adequate solution, we can stop our analysis right now and just assume it wasn't executed. If it doesn't get feedback, and do something, and we'd have to specify what it should do in the requirements. The feedback may be delayed. We could go on to determine why, or we could wait some predetermined time and then assume that it wasn't open. Incorrect feedback was received. Why? Well, maybe we assumed if it reached the valve, it would open, which is a common design error. So we might add a flow meter to detect water flow through the pipe, and so on. So what this does is generate new requirements and new design features. So we need to include feedback for the open and close valve commands. The software shall check for feedback, so we've got a new safety requirement for the software. It shall check for feedback after issuing an open-close command. If it not received in a specified time period, then assume the valve wasn't open or closed and do something. And that depends on your designers, what they want. There must be feedback to the controller to determine that the water is actually flowing through the pipe before issuing an open catalyst command, perhaps using a flow monitor. All right, so let me give you one other example. I said that this was this works on very complex systems, and my book on this didn't come out till January 2012, but I really came up with this idea 10 years before. It was so different than what people did. I was kind of hesitant to, I was afraid to tell people. I thought they'd think I'd lost my mind, and if I didn't know it worked. So we started trying it on systems smaller than this one, but a friend who had more confidence in me than I did, offered to do this for the U.S. ballistic missile system. MDA is the Missile Defense Agency. We're trying to find, they had to do a non-advocate safety assessment just prior to first deployment and field testing of this system. It is one of the most complex systems ever created. And nobody knew how to do that safety assessment. The hazard was inadvertent launch, so they didn't want during testing or deployment to inadvertently launch on a missile. So since nobody else was volunteering, they agreed that we could try, that my friend could, I didn't do it, my friend could try this on their system. It was done by 2 people over about 5 months. Most of the time they were trying to figure out how this thing worked. They found so many scenarios that had never been identified during the 10-15 years of development of the system that deployment and testing was held up for 6 months. And in many of those scenarios, all the components were operating exactly as intended as my component and interaction accidents. There were no failures, but the complexity of the interactions led to unanticipated system behavior. It also identified all the component failures that could cause inadequate control. But most analysis techniques only consider those failure events. So let me show you the high-level control structure, safety control structure for this system. It's called FMIS here, fictional missile intercept system, because the U.S. government sort of doesn't like me talking about the design of the real ballistic missile system. But there's a command authority up on the top left, which gives doctrine, engagement criteria, training, other things to operators. They get feedback here from the operators to make sure that this is all working. The operators send commands to the fire control computer. The fire control computer takes those commands, takes input from radars and their early warning systems of various kinds that the U.S. has for identifying that a unfriendly thing is flying at us, and then issues various commands like fire disable, fire enable, and other things to the launch station. The launch station controls the launcher. It also controls the flight computer, which controls the interceptor hardware. The only other thing in here is an interceptor simulator, because they know things could fail, hardware components could fail during this thing. They simulate and check these kinds of things during operations continually. Now, we know that actually these simulators are very dangerous. We almost launched on the Soviet Union once when data got mixed up. Simulation data got mixed up with real data, and we thought that there had been a Russian attack. Luckily, the humans overrode and did not launch in return. But since this has happened several times actually, um, they worked really hard at preventing those problems. All right, so here's some examples. I can't tell you the details of the scenarios that were found. They've all been fixed. What we found in those first 5 months. So here's some examples. The operator could do something strange but possible in terms of clicking buttons and stuff on there and doing things on their screen at the same time that the radars detect a potential but not dangerous threat. That could lead to the software issuing an instruction to enable firing an interceptor at the non-threat. It turns out the problem was a missing software requirement to handle this case. It was a perfectly legal case for the operators to do. They didn't think they would, but they didn't know. How do you guarantee? Well, you could try and tell them not to do it, but that's not a very effective way to do this. So the easiest solution here, I mean, there are other solutions, but one solution is fix the software. Now, if we'd done this early, you would generate the software requirements. You know, they waited here until the whole thing was finished, but we could have generated those early. Identified timing conditions that could lead to incorrectly launching an interceptor. If you, on the previous slide, there's two. There's a fire disable and a fire enable command. Now, these are sent on different communication lines. Let's say we issue a fire enable. Now we get information that the threat isn't really a threat. It's really a 777 flying between Heathrow and Boston. So then we issue a fire disable. But because these are on different lines and there was no protection in here, the fire enable and disable could have been received in the opposite order. So they receive a fire disable and then receive fire enable, which of course is catastrophic. Simulator data. We found situations, even though they tried to prevent this, were weird, odd cases where the simulator data can be taken as real data. All right, so that's the biggest example I'm going to do, and for those of you, if you're getting antsy, I promise I'll be finished in about 5 minutes. We can automate much of STPA because it's based on a formal foundation. We can actually have John Thomas, who's one of my brilliant PhDs, finished a few years ago, and we can take the hazard. You can just give them the hazard, and it will create that matrix, that table you saw, automatically. And we put it goes and gets changed automatically into a discrete mathematical representation, and then it can generate formal model-based requirement specification. We happen to use this one, Spectrum RL. You could use other ones if your model allows this kind of thing. But that allows automated completeness and consistency checking, and so we can guarantee completeness. Now, of the unsafe control actions, the scenarios, we're still working on that. You still have to be done by humans, and in fact, one of the things that happens when we generate them automatically is we get too many of them. Some of them just physically impossible, but the computer doesn't know that. So a human may have to cull some of these out. But there is, as I said, now automated tools being built. This is another brand new one I talked about, Dr. Cody Fleming. He's now at the University of Virginia, a professor in their system engineering there, called System Theoretic Early Concept Analysis. What we really want to do is do things early. So he can take a concept of operations document before you've actually done any real design on the system, generate a model from it, and use model-based analysis to identify unspecified assumptions, missing, inconsistent, incomplete information, vulnerabilities, risk trade-offs. We can generate system, software, human requirements, including information requirements, and it can do architectural and design analysis to eliminate and control the hazards. If you look at this curve, this graph here, what you see on the x-axis, we just have the stages of development: concept, requirements, design, build, operate. And on the y-axis is effectiveness and cost. And as we all know, finding a problem early, it costs almost zero to fix. As the later you get this increased cost of rework, of changing a problem that you've already had, becomes astronomical. It becomes enormous. It goes up exponentially. So, but all of the things that we do now work late. Preliminary hazard analysis is after the requirements, just right before design. System and subsystem hazard analysis is done after the design is built, just before build. And then accident analysis, of course, is done late. But we don't have anything until now for up here, and that's where STECA and STPA. 70 to 80% of safety decisions are made during the concept formation stage. If we can find the problems then, it costs zero to fix it. Safety engineering doesn't have to be expensive. It can be free if you do it, or virtually free, if you do it in your early system engineering phases. CAST is an accident analysis technique. It provides a framework or a process to assist in understanding the entire accident process, identifying the systemic factors. That's after an accident has occurred. The goal is to get away from blame. Who? Because we get nothing out of blame. We say, okay, the pilot's to blame. Next, pilot's either dead or the pilot's you fire them, and it doesn't really solve the problem or how to prevent future type accidents. And we're having very similar accident causes over and over again because we just keep blaming the pilots or whatever operators. We try to reduce hindsight bias. Hindsight bias is after the fact. It's easy to see what the operator should have done. It's very hard at that time for the person at the time to know, doesn't know the future, and so hasn't all those connections, causal connections in their mind. So the goal of CAST is to determine why people behave the way they did, not just to look at what they did wrong. That's easy, but why did they behave the way they did? Why did they do it, which in hindsight was wrong, and the weaknesses in the safety control structure that allowed the loss to occur. This has been done on lots of accidents, several of them in my book, but there's lots of others. This was a aircraft. I think I'm going to, just the name of time, I think I'm going to skip this if anybody really wants me to come back. This also applies to security. This is a PhD dissertation by Air Force Colonel Bill Young. Today's cybersecurity focuses on tactics. It's framed as a battle between adversaries and defenders, and it requires correctly identifying the tactics of the attacker's motives, capabilities, targets. Very, very hard to do. What you want to do and what we can do is reframe the problem in terms of strategy, identifying control system vulnerability versus reacting to potential threats. It's a top-down strategy versus a bottom-up tactics approach. Tactics have to be tackled, but we do those later. And so what you can end up with is an integrated approach to safety and security. So safety is preventing losses due to unintentional actions by benevolent actors. Security is preventing losses due to intentional actions by malevolent actors. The key difference is intent, but intent doesn't really matter in terms of preventing these things. Our goal is to prevent losses, and that's a common goal. So in networks, you know, we often try and say, well, we'll just try and keep all the bad guys off of the network or off of our computers. You can't do that. It's not going to, it doesn't work. We've already seen that. Breaking it will almost multiple times a day. What we really want to do is ensure that the critical functions and services provided are maintained. I don't care if they get on my network if they can't do anything harmful when they're there. This new paradigm for safety that works for security, it absolutely, like STPA, looks the same at the beginning. We have to add some new causes because the causes we looked at were inadvertent causes, and now we have to add things like the operator does this on purpose or somebody does a denial of service attack, but the rest of the process is the same. And again, it's a top-down system engineering approach to identifying safety and security in systems. So again, we can look at this curve of these different types. Security is usually often attack incident, accident response. We may add some bolt-on during the build process. Almost never is security handled during system engineering. It's certainly virtually never done during requirements and during concept development. But we can do that now with these tools. So how is it being used? First of all, is it practical? Well, it's being used in a large variety of industries, just about everything you can imagine. I've put some names down of automobiles because they're pretty open about it. Part of the problem is people don't like to talk about what they're doing publicly in safety for various liability reasons. But GM, Ford, Nissan, Toyota, and we think others who also aren't talking about it, we're getting information that they're actually using this. Medical devices, chemical plants, just about everything you can imagine is using this now. But we can also being used beyond traditional system safety. It's been applied to quality during development of systems development. It's been applied to producibility of aircraft by someone at Boeing. It's been applied to nuclear security. It's been banks and are writing me and telling me they're using it. I don't know what they're doing, but they tell me it's working. We've applied it in engineering optimization in optimizing the system engineering process in a very large company. I'm using it, we can use it for looking at and changing and analyzing organizational culture. It's starting to be used very successfully now in workplace safety. We tried it and it's within one company it's gone viral because it's working so well. All right, does it work? Is it effective? Well, in all cases where comparison was made, and comparisons usually are made, most of the time people aren't going to throw out what they've been doing for 50 years and what is in every standard and required for the standard, just on the basis of, well, Nancy Leveson says we should do this. So what most companies are doing is creating demonstration projects or parallel projects so they can compare it to the standard techniques they're using. In every case that we know of, and there are dozens of them now, STPA found the same hazard causes as the old methods, plus it found more causes than the traditional methods. And these are usually related to software and humans and other things that the traditional methods sort of ignore or treat superficially. We have two new technical reports just this month and the last week. One is on a helicopter, an existing helicopter, the Black Hawk, although it's an upgrade to the Black Hawk, and we did it on the caution and warning system for including the electrical and flight management systems, and we compared it to the actual official safety analysis report given to the Army by their contractor who was building these and designing these Black Hawk helicopters. And we found, you can read the results, but the same thing happened. We just finished one again last week. for the Navy on a dynamic positioning system with the same results. Both of these systems were using 882 and 4761, which is commercial aircraft standard. Lots of stuff being done now in the automotive industry and comparing it to 26262, and there's a lot of promotion by people in the industry to include STPA in the 26262. I don't follow a lot of the standards efforts, so I'm not sure how it's going. In some evaluations, they found accidents that occurred that the other methods missed. EPRI is the electric, why am I blanking? Research Institute. I can't remember with the P. Maybe it's on, tell me later in the question period. Anyway, it doesn't matter. They're a research group that the people who run, operate nuclear power plants belong to, also other kinds of electrical systems. And they did a blind study where they gave a design of a nuclear power plant, and they gave they had experts do a fault tree analysis, other experts did a HAZOP analysis, other people did a FMICA and FMIA on it, somebody else did event trees, everything you can think of they had, and then they had hired a couple of my students for 2 weeks to do this in STPA. And the result was, it turned out there had been an accident in this nuclear power plant, a really serious accident that they haven't really told the public about because nobody was killed and didn't have to, but it was very concerning. And it turned out, and none of the analysts, of course, knew this. We didn't know this. None of the other people knew it. And in the end, only STPA found that accident. There have been other cases in the same way that STPA found the accidents that the other methods missed. What surprised me was the cost. I assumed because it was so much more powerful than the things people are doing now, that it would be more expensive. And I had an argument already for why they should pay more for it. It's turning out in every case to be orders of magnitude less expensive and require less resources than the traditional hazard analysis methods. And I understand this now and why, but I haven't got time to explain it. We can talk about some other time if you want. The same results now. The securities have been evaluated by U.S. Cyber Command, Cybercom. They've already issued policy to adopt it for cybersecurity by the DoD, and it is being widely adopted in the DoD. So summary, this is a more comprehensive and powerful approach to safety and security in any emergent property. It includes the social, organizational, operator, software-related factors as primary components in the analysis. It's a top-down system engineering approach, and it handles much more complex systems than traditional safety analysis, and it costs less. So there's a book about it, came out in January 2012. It's by MIT Press, Engineering a Safer World. There's a workshop. We've been having them ever since March 2012, right after the book came out. There'll be tutorials, presentations, usually there's between 200 and 300 people attend, and I already have 200 people signed up for this year, so that'll be true again. There are also lots of information and lots of papers, theses, technical reports, lots of worked examples. There's actually a primer on STPA, which is a little out of date. As we learn more, I get better at teaching people it. But it's available. All of this stuff is available free for download. So, sorry I went a little bit over, but I am finished now.
No worries, Nancy. I mean, if you want to, add a few extra things to it, you're welcome to.
Well, why don't we open to questions, since I didn't allow anyone to ask a question. I was afraid we'd get, sophisticated questions at the beginning before the other people had heard, even knew what. Some people don't even know what stamp is, had no idea what we were talking about, and they wouldn't have understood the answers. So, but now we can ask questions.
Well, we do have a few questions already. So if you want to familiarize yourself with the questions in the questions window, I've addressed some of those while I've been at it, and then I'll talk to people about the other resources, and then we can do questions. So I'll just take the presentation back, and then if you look at the questions list, right? Okay, I think it's working now. Hello, everybody. Okay, so there are some other resources available. Nancy's already mentioned her book, Engineering a Safer World. Everybody who's registered should be, intimately aware of that book now, and especially the link to the chapter that I suggested reading beforehand. Now, there is the MIT Partnership for a Systems Approach to Safety, PSAS website, where you can go and get extra information about STAMP, and also access to this year and previous years' MIT workshop presentations. There are also some videos on there as well if you have a look at that. Nancy's got her own website, sunnyday.mit.edu, and that has a lot of papers and links to presentations and books and such like. And then there's also the LinkedIn group, the International Stamp Interest Group, where you can go in there and get information about what's sort of happening and general discussions. So we're starting a bit of a community there. As Nancy mentioned, there is the MIT Stamp Workshop in Boston at the end of March. It's 4 days. It's a free workshop. You can get further information at the following link. You can also register. There's a registration link.
Could I interrupt for just 1 second? Please register if you're coming. I never know how many people, and the first time I ran this, I expected 50 people, and I got 200, and had a little trouble figuring out what to do with all these people in terms of rooms and food. So if you could register, it's free, but it helps us understand how many people are coming. The other thing is, on the website, we have most of the presentations from all the previous ones. It's really not a conference, it's a workshop. People just come and talk about what they've been doing, but so we don't have a formal proceedings and papers, but we do have all the presentations, most of them, up there.
I'll just add, I'm fortunate enough to be accepted, so I'll be doing a presentation on enriching bow tie analysis and using air traffic control as the example. So if you'd like to know more about that, just get in touch. There is also the European Stamp Workshop, which this year has been hosted in Switzerland, in Zurich. Now, as far as I'm aware, the guys haven't set out a pre-registration page, so I've put a link there so that you can pre-register, and then when they're ready to start accepting registrations, I'll send an email to you guys, and then you can go and register if you want to attend. There is also
let me just, okay, I just want to interrupt front. I don't have put a hand thing that I can raise. So let me just say that I don't have control over the European one, and the Japanese one are all done by other people, so I don't have any control over them. I just want to warn you that they're done, so they may do with them very differently. Some of them have papers, some of them have fees. We don't. There's also, as he was just about to say, one that's going to be in Japan, run by the Japanese government agency in December 2016, and that one also I have no idea. I've been invited to these, but I have no idea I'm not helping to plan them. We've also heard that Brazil is talking about starting one of these. So as you can see, there's a lot of the Embraer people. So as you can see, there's a lot of interest around the world.
Yeah, just to add to that, I'm a member of the conference committee for the European Stamp Workshop, and I presented back in Amsterdam when it was back in October when it was held in Amsterdam. So if you do want further information about that, just drop me an email or register at the link, and then when the time comes, I'll send you an email. Yeah, and so also myself and Nancy are going to organise 2 UK-based events programmed for October 2016. And at the moment, we're looking at potentially doing 2 events back to back. One will be an introductory event, similar to this one, but more specific to the people who are attending. And then also a mastermind workshop. That's just a name. We don't know what we're going to call it yet, but that will be more detailed. That will be more specific to the attendees. So if we get a number of attendees that are focused on, say, the automotive industry or air traffic control or medical healthcare, then we will focus on those, and the course will be around that. So please register your interest at the following link. I have tried a little bit of other technology, which is a text. So you could text UK event to that telephone number, and that'll register you, and then we can, let you know as the organisation, the planning takes effect. We can give you more updates. And then also, if there's any other UK-based events sooner than October that might be more appropriate, again, just register your details, tick the box, let me know, and we'll see what we can sort out. Okay, now, myself and Nancy had a bit of a talk on Tuesday, and we've already sort of established that there is a lot of interest in the webinars, and we are thinking about perhaps running another webinar or perhaps a series of webinars. So if you're really interested in that, and if there's anything specific, a particular topic that you want addressing, then please go to that address and let us know what we can do for you. And then finally, questions and answers. Okay, so just a reminder, on the screen there is a box for your questions. Type it in there. Myself and Nancy will go through the list and address the ones that we can do in the time that's still available. Okay, so Nancy, have you got the questions screen up on?
So I do. It's a little hard to get to them because it's only one line at a time, but I looked at a couple of them. One of the questions relates to the issue of dynamic control. Could it be used for analysis of systems whose behavior changes at runtime? That is, the dynamic behavior is autonomous. Oh, perfect for that kind of system. That's exactly when you need a control system. Think about it. Control theory is exactly that. Control theory says we control things and we get feedback and we control their behavior without necessarily knowing beforehand, being able to predefine what their behavior is going to be. This is absolutely perfect for that. We have examples of systems of us doing that. Somebody asked if it's possible to get a copy of this presentation. Sure. Similar ones are up on the website, but I'm sure that Simon can figure out how to, it's fine with me.
Yeah. Okay.
But we already have some in the past workshops, because I do a presentation like this at the beginning of each of the workshops during the tutorials. Let me see, let me go backward. I have to leave on the dot for another meeting. Any leads to automotive resources, really welcome. Yes. Oh, somebody is already a convert. Oh, wonderful. We've been doing a lot of automotive. It turns out the automobiles today have 100 million lines of software in them. They're astoundingly complex. They're much more complex than jet fighters. I mean, we're doing this on military equipment, but the autos in reality are actually more complex. And so we've been doing this for years. We have lots of contracts and with automobile companies. Many of them are talking to us now, are at the point where, okay, how do you help us train all of our engineers on this? It started with just research. We've shown how to fix things like deal with things like the feature interaction. They keep adding new features on the automobiles, and it turns out each of them is safe in itself, and you put them together and you have horrible things like you get out of the car and the car takes off by itself, and weird things. So we can identify them and we can actually deal with these. Let's see. Many messages really resonate with me. Oh, I think I already answered this one. Are there ones, let me see if I don't know how to get, Simon, are there other ones I
Yeah,
can't see that?
there's a few. If you scroll up the right-hand side of that window,
Oh, okay,
you,
where can we learn more about the security variant? Very good question. We have a paper, a couple papers up in the website. There's not a lot. We're doing more and more with security. There have been lots of demonstration projects, but as you can imagine, they're classified. So it's very hard. We have a general paper that explains it and how you can do a integrated thing. And it's very short. It's only about 6-7 pages, so it's blessedly short for me. But most of the examples are unfortunately classified. This is being done by the DoD on some of their missions, really most secret missions. But the dissertation I talked about is going to be finished in a couple weeks, or I murder him, because he's really taking too long to finish this. He's so busy teaching people. But the dissertation has scrubbed examples, and we're going to try and get more of those out. And of course, this dissertation will be available as soon as he finishes it, and I accept the final version. Let's see, Swiss cheese model. Have you considered any synergy be your tools related to organizational accident theory? Okay. Well, the Swiss cheese model is the old reductionist approach. It looks fancy. It's just the old domino model. Each of those barriers is a failure, and there's some randomness about whether the holes all line up. It's just a chain of events with random failure in a much more sexy, pretty method. And if you notice, at the end is always the actor, the pilot is blamed for everything. I mean, James Reed's a psychologist, and the wings could fall off the plane, and the pilot will still be blamed in the Swiss cheese model. And in human factors and analysis methods like HFACs that come from it. So there's not really synergy with that. Organizational accident model, accident theory, I think much of it is wrong. It's done by management types like high reliability organizations. I can tell you the organization, the company that uses high reliability organization theory to the T, they have a vice president that makes sure they do everything in it, and that's BP, which is the worst accident record in the world. It's never been validated. We have a paper on the website describing why it's wrong, in case you're interested. But we are doing a lot of organizational analysis. The first one was about 10 years ago on NASA. After the Columbia, NASA introduced a new organizational design for safety and managing safety in the shuttle operations program, and we did a risk assessment for them using this stuff. It was very early. It's on the website, but it's very early, so it's not as sophisticated as the ones we do now. I just finished one. I have to be very careful about what I say, for a very, very large aerospace company, but there's many that fit in that category. And we did it on their engineering organization, and it's working great. They are so excited about it and how to change. We did a cultural analysis to understand what changes need to be made in the culture in order to get better results from engineering. Are there more types of complexity? Actually, there are different types of complexity. I've done that, talk about that sometimes. Interactive complexity is one. Another type of complexity is dynamic complexity. One of the questions earlier was about dynamic nature of systems. Because things are changing dynamically, that makes things much more complex. We can handle that. I've given some talks, academic talks, about the types of complexity. But I'm not sure that we need to go into there. What about human performance variability and modeling it? Absolutely. So what we can do now, what I showed you now, is really situation awareness. That process model, in humans we call it a mental model, is really related to problems that occur in situational awareness. And we can identify those beforehand and when they might be catastrophic, and how we get the information and make sure to the human and make sure they notice it and can process it. So we're actually doing a lot in situation awareness, but we're doing more now. We're looking at mode confusion for humans. We're looking at and how do you design the software, so and the avionics systems that we're having to do it for aircraft, but we're also, and also air traffic control we're working on. But you can do it for any system, and I have several of my PhD students are interested in human factors, so we're doing a lot more human factors stuff now. Another PhD dissertation will be finished in about 6 months is coordination. How do you coordinate, and this is an Air Force major, he's a fighter pilot in the Air Force. How do you coordinate automated systems and pilots? They're working so closely together on these things. And how do you coordinate the decision making when you're flying an airplane? And how do we get that into the hazard analysis so we can do a better job of designing for it?
Hi Nancy, just to add to that, do you want to tell everybody about your visit to the UK during April to the is it Human Factors and Ergonomics event?
Oh yeah, there's some kind of keynote talk I'm giving in April. If someone asks me, send me mail. I don't remember. It's in some small town in England that's going to be very hard for me to get to. Thank you for helping me. I'm not a great publicist for myself. How can STAMP be applied in drug development, clinical research? We have done this in clinical drug development. We have a paper up on it. We analyzed the Vioxx problems in the United States. There's some of it actually in my book, a little bit about that. There are this year's workshop. There are 2 healthcare-related presentations, one on drug development by some Europeans and one on cancer diagnosis in the UK, National Health System. I've been working with hospitals now in the United States, and we're doing a lot with checklists with safety in hospital procedures, radiation therapy. So there's a lot of stuff. There is stuff being done. What are the main challenges you encountered in this domain? To be honest, the main challenge is doctors and people who already think they know everything about safety. And so they say, well, if we just fire all the bad doctors, then that's the problem, and all of you with your system stuff is just nonsense. That's the biggest problem we have, but it's a cultural problem, and we have published papers now in the Journal of Patient Safety and the Journal of Thoracic and Cardiovascular Surgery, because we've done it on some surgical systems at major hospitals. We have some stuff on radiotherapy coming out. Will the slides be available? Yes. With the oral spoken text? Well, yes, if the recording. This is our first time doing a webinar, but we've been promised the recording will work, right, Simon?
Yeah, about.
So we'll tell you after we finish this and go try and play back the recording. So theoretically, yes, it will be available with the oral text from Nancy. How does your approach handle hazard analysis of controlling actions, interactions take place at different levels of abstraction? appear in the concept and appear in the component. May affect, this is a long question, may affect high-level ones and vice versa. It's a hierarchical structure. So the fact that things are at different levels of the structure doesn't matter, because eventually everything at the bottom is controlled by every level up above. But it's controlled more indirectly, and the timing's different. The lower levels, the timing, the control becomes very tight within minutes, whereas when you start getting at the higher hierarchical levels, the control actions are more at the months and years level, perhaps. So it's a different timing, but in the end, everything, that's just basic systems theory, everything is controlled. Okay, so I know this was a basic. Next question.
Sorry, Nancy, can I just add a little bit to that last question? If I take the intent appropriately, if, for example, you were, I don't know, operating a nuclear facility, and during the design or concept phase, you would develop the high-level control structure, identify high-level safety requirements, safety constraints, and then they would flow into the design. When you actually change your project phase to, say, installation or bringing on site nuclear materials, then obviously your control structure will be different. And so you could then model the new control structure, identify any new or changed safety requirements or constraints, and then make sure that they're put in place. So your control structure may change depending on the phase of the project or the system operation that you've got. And STAMP allows you to model all of those control structures, and then where they can potentially change or even degrade depending on the phase of the project. Just one second.
Okay, good answer. The next question says, I know this is a basic introduction, so maybe be clearer when I understand the process more, but it seems to be an extension of traditional methods rather than a replacement. Is that correct? I think it's an extension of the causality model. A causality model is a formal, kind of a thing in your mind about how you think accidents are caused. The Swiss cheese model is not a method or a technique, it's a model. And this is a model of causality. And the way we attack the problem depends on our model of why we think the problem occurs. Why do accidents occur? So it is an extension in that respect, because the old model says accidents are caused by chains of failure events. This says that's not enough. It's only a subset, and we need to expand the model of causality now that we're getting more complex systems. Models are just models, and the old model used to be fine. Now, it's not an extension of the old techniques that were built on them. Because, for example, fault trees are built on this failure model, you can't use fault trees to find these kinds of problems. That's why in the APRI study and other things, we were the only ones that found the accidents, and this is why we're finding more than all of the others. They're all based on that old model. So you can't expand that, but you can certainly expand the underlying causality model, and that's what it is. Not a question per se. I'm afraid I have to leave due to my next appointment rapidly approaching. Oh, thanks. I won't have future events. Are there any free access models to the process mentioned? Yes, there's a free access model on our website for STPA. Again, I need to update it, but I never have any time. But there are lots of papers, as I say, and the technical reports go into how to do it and have lots of worked examples that are all on the. Cybersecurity traditionally uses a system engineering approach. It's difficult to tell what's different about STPA from the published work. You need to read You need to read. It doesn't use a system engineering approach. It uses a bottom-up fault trees are just attack trees. It uses this bottom-up reliability engineering approach. But I'm not going to be able to explain that to you in just a minute and without being able to draw pictures and spend 30 minutes an hour trying to show you what's different. It is totally different when you see it than what's done now. And as I said, that short little paper by Bill Young and myself on our website should help with that. I come back.
Sorry, Nancy, is that something that we could perhaps have as a topic for a future webinar that's more focused on cybersecurity? Perhaps.
Perhaps what?
Do you think that could be a topic of a future webinar, cybersecurity?
Oh, yeah. Oh, absolutely. I mean, I can bring other people in. I can bring my student who's wonderful, Colonel Young. Somebody suggested Googling STPA-Sec for the paper. So apparently you can see it. All of these are not really questions. What's the difference between AxiMap and accident analysis based on STAMP? Oh, that's a wonderful question. I am a great follower of Rasmussen. Jens Rasmussen in Europe really is sort of the father of, in Europe at least, of this kind of systems approach to safety. And in the US, it grew up in the missile defense industry, but nobody ever heard about it outside the industry because everything was sort of secret. Jens wrote more public papers. And AxiMap comes from Jens' idea. It's a subset of, I expanded Jens's model that AxiMap is based on. And there's a little in my book about that, how I extended it. There have been some comparisons with AxiMap, and there's some advantages in that everything fits on one page usually, but the problem is it fits on one page because so much stuff is left out. So I think that it's better than AxiMap. The Dutch Safety Agency, which is like the National Transportation Safety Board, the NTSB in the United States, did a comparative analysis, AxiMap, STAMP, or the tool called CAST, and some others, and decided that they liked CAST the best. So you'll have to see. Hello, Embraer's STAMP research. Oh, somebody here, working group is already here. Aha, saying hello. Both considering system theory, aren't they? Both what? Do you understand that question?
I think it's a follow-on from the question about AxiMap. So what's the difference between AxiMap and CAST?
Absolutely.
And
they are both based on system theory, but the model of causality in STAMP is expanded beyond that of the model of causality in Rasmussen's original model, which was in his 1997 paper. I actually just published a paper on this called The Legacy of Rasmussen. I didn't talk about AxiMap directly, but I did talk about how all this comes from Rasmussen's theory. If anyone's interested, it's up on my website. But they are both systems theory, and I certainly think AxiMap is much better and much better than the things people are using in root cause analysis, which now are basically chain of event models that you just follow back in the chain until you find someone you can blame it on, and then you stop following it back and you label that the root cause, usually some kind of operator. I talk about that in the book. So it's just, I think that we've expanded and we find more causes, and we have a structured process in CAST that you follow and you get more out of it. Great to have a talk on different types of complexity.
Nancy,
Am I supposed to be seeing?
Sorry,
Oh,
Nancy.
someone's
Could you make a comment about bow tie analysis in the context of what you've just said about cast?
what kind of analysis?
Bow tie analysis.
Oh, a bow tie is back in 1970. It's one of those old methods. All they did was tie a fault tree with an event tree. You know, tie a forward chain with a backward chain. You're going to miss everything on that. I've seen those. The process industry uses them. The petroleum and gas industry has been the hardest nut to crack in terms of getting interest, and I just ignored them. I have enough going on. I didn't really need to go chase people who didn't want me around. But they're starting to come to me, and because bow tie has serious limitations, and bow tie is the oldest, naivest type of thing, and it's going to catch almost nothing in terms of systemic factors. It's just a chain of events, forward and backward from some point. Oh, Simon's going to give a talk on this, isn't he? Are you going to say you like it?
Well, I don't want to upset too many people that use it, but personally, I think it's a complete waste of time, and everybody should be using STPA and cast. But that's, I won't be too controversial about it.
Okay. When you know the analysis is complete. Great question. How deep should we go in the analysis? How can we deal with a very complex system in terms of time and money, such as analyzing a whole nuclear power plant? Thank you. Great question. All right. A bottom-up technique like a FMIS is enormously expensive and not very effective because it's bottom up and you have to look at everything, and eventually you just run out of resources. You can't look at every failure and see whether it leads to a hazard. A top-down method, including fault trees, but STPA's top-down is much more efficient. So how do you know it's complete? Well, fault trees only look at failures, but you don't really know when they're complete either. With what we found in STPA is you keep going down and looking at more causal scenarios or more causes as long as you don't have a solution. When you have a nice design solution for the thing, it doesn't really matter that you get all the causes. If I can solve the problem by putting in I don't know, an emergency button or something, an emergency stop button, then I don't necessarily need to eliminate every single and identify every single one. So this really allows you to tailor the amount of work you do with what you really need to do and the minimum you need to do. How can we deal with very complex systems in terms of money? Well, I showed you the missile defense system, one of the most complex systems. I mean, not only includes all the radars and all the launchers, it also includes all the shipboard stuff like Aegis, which runs submarine launcher systems. I mean, but what you saw was a very high level control structure, right, for that ballistic missile intercept system. Now, what we can do is see, is there any possibility of this thing causing a problem? Can we just add, for example, a new case in the software? Or do we have to go down more in depth? And you may have to. If you can't afford to do more, then you have to figure out a way to just deal with it in the best way you can. At that point, you may have to stop and say, okay, we're going to have an emergency stop, or we're going to call for the Coast Guard. And we're not necessarily going to prevent every type of way that this ship could sink, because it really depends on how expensive, how costly and how catastrophic an accident is as to how much you can spend. How do you analyze a whole nuclear power plant? We've done that. We've got a research report, and we didn't do the whole plant. We did the shutdown system, which is what they certify on. This was for the Nuclear Regulatory Commission. We've gone into nuclear people who are building nuclear power plants. Large utilities, can't give any names because we've promised anonymity to them, and they're doing it on their systems, and they're finding again much more things that they just didn't know about. In fact, one was close to releasing a system. And we went in just to give them a demonstration, and sometimes when we go into a company, we'll have them work on their own problem just to show them that are part of their problem for the day. And in just that 1 day or 2 days that we did, they found some catastrophic problems in their system, potentially catastrophic. Now, I can't tell people what to do. We were doing teaching, and they were really concerned because this thing was going to be released in 3 months, and now they found stuff that they didn't know about and didn't expect. And what they did about it, I don't even know. And but yes, it can be done on large, very complex systems like a nuclear power plant.
Just to add something to that, Nancy, I have said to a few people that have decided they want to have a go with STAMP, STPA, and CAST, and it has to be clear at the outset that when you start using this method, because of it is very powerful, it is likely that you'll find unpleasant surprises, or you'll confirm things which have been suspected. And so when this analysis is done, just be prepared that you might find something, that then needs to be appropriately dealt with. Instead of running around blaming people for not doing the analysis properly in the first place, or pointing fingers, focus on fixing the issues that have been identified. In fact, in the advanced event that we're going to run in October, we haven't decided yet what form it's going to take, but it is likely that if a particular organization wants to send a few of their team across to talk about a specific real example, we don't have any problem signing any non-disclosure agreements and working through those examples live.
Yeah, we do that too. I mean, but I've gone in, and what's surprising me is sometimes people will tell me, we can't use this because we're afraid, our management is afraid we'll find things we don't know about. And our lawyers tell us that we'd have to do something about it. So we can't, our management, we want to use it, but our management won't let us. This is part of the organizational problem and culture that I can't deal with. I want to write a book. One of my next books is going to be about, workplace safety, because we're doing a lot on that, but then also on why safety pays. I mean, management just doesn't understand that safety in the long run pays. It costs an enormous amount if there's an accident, and even finding problems late, basic design problems you find late in the development process during maybe system testing, the cost of making changes at that point can be absolutely enormous and maybe prohibitive. So you put in a little extra redundancy or something because you don't know what else to do, and you have to release the system. And this is why I'm in a university. I don't have to make those kinds of decisions. There's for wiser people than myself. I just tell people how they can do things and should do things. Whether they do them or not has to be up to them. The next question says, can the STAMP part on accident analysis process look at less critical occurrences for aircraft? Oh, sure, any occurrence. Or precursors. Yes, I have a paper on leading indicators, how to identify beforehand precursors so that you can identify when your system is drifting towards states of higher risk. Most accidents, this was a concept by Jens Rasmussen, so this is an original with me, but systems tend to migrate, tend to change over time, and they tend to get more risky as they don't have accidents. People start acting in a different way and making decisions in a different way, and you're under a lot of competitive pressure, production pressures, and so people start to act more risky, and they don't know that they're doing this. And so we can identify, we have a way of using STPA to identify leading indicators of risk. Assess updated probability of accidents. I didn't get into this because it's so oh good, at least half people have already left, so I only offend half of you. This is a religious argument, but I don't believe that it's possible to know what the probability of an accident is. I don't know what the future is. The things I can measure and have a probability for, which is hardware failures, are usually not the cause of my accident. I have been involved in large accident investigations, small one. I've read hundreds of accident reports. Every single one of them had a probabilistic risk assessment that showed that accident could not happen. And in fact, one of the contributing causes was then they didn't do anything about it because they proved it couldn't happen. So many of those probabilities are just wishful thinking. Sometimes they're based on politics. You want to do as little work as possible, so you make the likelihood as low as you can. We have in in the Blackhawk helicopter one I told you we just published, we found lots of things that they had said likelihood was marginal. The risk was really low of an accident, so they didn't have to do more. And we, using STPA, found past the catastrophic accidents that were perfectly reasonable. And we compared that. So I'm not sure I believe that we can even know what the probability of an accident is. I just don't have a crystal ball about how people are going to behave in the future, how the environment's going to behave in the future. We can try and predict these things, but we're not very good at it, to be honest. There's something called heuristic biases, and they make and basically it's a scientific psychological principles that say that humans are really bad at estimating probabilities and risks. And identify actions to be taken before the accident occurs, absolutely. And that's what STPA is. I mean, you either look at an accident after the fact, identify all the causes, and then try and fix them all instead of just blaming it on the operator, firing him, say we'll train them better to not make that mistake. Or you can beforehand identify and prevent the accident. Okay, is it possible to have a talk on how to address organizational culture? Absolutely. I haven't written this up. It's so new. I'm in the middle of writing a paper on it, but yes, definitely. Simon, could you please collate links? Okay, these are all.
Yes, I'll be doing that in the post-webinar follow-up. So I'll be sending an email out with all that information, and also I'll send out a post-webinar survey. So if you'd be kind enough to fill that in, I'd really appreciate it.
I have somebody saying hello to me, but I can't see his full name. And hello, Simon. All right, how do you know we are applying the analysis correctly? Well, that's a good question. That's true. Most analysis methods, most of the fault trees I see are utter rubbish in practice. People aren't very good at that. I guess you need to get some training. I'm not sure how to answer that because I don't know how to do that for any analysis method. how do you know you're applying it correctly? Um,
I could add,
uh,
I could add something to that. Um,
yeah, please.
when when you're creating the hierarchical control structure, you're modeling your system. Um, Essentially, it's intuitive. So depending what you define as your system and who the different people are that are involved and the different technical aspects, when you put that model together, you will get a good feel as to whether that is a reasonable model. And so when you analyze that model and you cover all the bases, effectively that shows that you have a complete analysis. But obviously, you've got to keep in mind that models are useful, but all models are wrong. So as long as you recognize those limitations, then you should have a good quality analysis.
Oh, that's a good answer, Simon. The other answer is that you never just do, I would never have a safety analyst, and including myself, a safety engineer, just go do the analysis and say it's done. I always go to experts on the system. The expert engineers need to at least be able to review these things and say, yes, that's right, no, that's wrong. One of the things in workplace safety, a revolutionary idea, we actually ask the workers why they would make certain mistakes and what mistakes they make. It was amazing what they came up with. They know, but usually we engineers who've never put a plane together or an automobile together, assembled one, think that we can do all the analysis for the people who are actually doing it, the real experts, and that's just not realistic. So we should always have other people reviewing our analyses and real experts on the system to make sure that the analyses make sense. Does Nancy or have I know or collaborate with somebody who I've never heard of? Sorry, I've never heard of that person, so they want to know what I think of his take on human stuff, but I've never heard of him. Major problem is that you get no feedback regarding how successful it is. Accidents do not help, of course. Does STAMP consider this? If so, how? Absolutely. That's part of my leading indicators too. Let me give you an idea. I define leading indicators as failed assumptions. Accidents occur often, usually, when you tried to build a safe system and you made certain assumptions about how it would behave or what would happen, and you took care of those. And usually you took care of them okay. Accidents occur when the assumptions you made during your development and design and operations aren't realistic. So what I mean by a leading indicator is a check to see whether your assumptions that you made in your analysis actually are still true. And so yes, we absolutely do consider the issue of looking at feedback on how successful it is, and it's part of our whole process, in fact, built in for building leading indicators and risk management, and part of my new risk management ideas. Is there anything else? Recommend any books for starters, especially STPA. Well, the first starter is my book. Engineering a Safer World is really the basis for all of this. Now, STPA was still being developed at that time. It's not the best reference for STPA, but it's definitely a reference for in general. We have a primer. We haven't created any books because as we learn, we want to change it. One of the problems with writing a book is then you find out something needs to be changed and you can never change it. So we have a living book on the website, and that's all I can really suggest. And all the papers we have, lots of them. What is the paper on how to identify precursors? It's up on my website. Thank you for elaborating. Precursors mean on identifying tends to go toward Rasmussen's boundary of safety. Absolutely. So someone has read Rasmussen, and said, and asking, I think asking, is this what I mean, what Rasmussen meant by going toward the boundaries of safety? Yes, but I don't think of them as quite boundaries in quite the same way. It's constraints that aren't being satisfied. So I define it, the whole thing, using a very system theoretic method, is we're identifying constraints on the behavior of the system, and when we don't enforce those constraints on the behavior, then we start going toward accidents and increasing the likelihood of accidents. All analytic tools have limitations. Are there any other approaches you think pair well with STPA to maximize coverage? You know, I wish there were more new techniques. Most of what I see is people in universities who have never tried it on any real system, never used it in the industry, and frankly have never worked on a real system, and they make up some kind of new tool, and nobody ever uses it, and nobody ever has used it. And most of them don't seem very useful to me. You know, I worked in this field for 36 years, so and on real systems. I have always worked outside the university and worked on various kinds of really complex engineered systems. So I wish there were better other tools. Most of the stuff's old. HAZOP, we've seen that STPA just replaces HAZOP and FMIS and others. I don't know whether they want me to say their name. They said this at a public meeting in Japan, but I don't know. One of the Japanese companies said that they traditionally used FMIS. When we first met with them and showed them how to use STPA, they said, well, we're not going to give up FMIS. We'll use this in addition. And we said, fine, whatever you want. All we're here, you asked us to show you how to use it, we're telling you. And last year at a meeting, another meeting in Japan, someone from the same company stood up and said, we're not going to do FMIS anymore because we found the STPA finds everything done by FMIS, and FMIS is so expensive. So I can't answer that question. I wish there were some better tools to use. We have tools at different points in the life cycle. STECA is probably most appropriate very early in the life cycle, STPA a little bit later, although still in the early design stages. I wish people came up with things that I really liked. I haven't seen anything that I thought worked because they don't seem to have any theoretical model underneath what they're doing that justifies what they're doing. They just make up something and say, well, you know, I like event network analysis, so I'm going to claim that we can do a network safety analysis using network analysis. Well, why? I mean, there has to be some rationale connecting this network analysis to the cause of accidents, or you're just writing a paper. So, sorry, I think that's the end.
Well, there is I mean, we can end it there, but there are a few questions that arrived during when you were talking. So we can, I think there's probably 4 or 5 of those that we can just quickly jump to. If you scroll up the questions window to 1426, Frank, he's asked a question about the SIL concept, which I think is worthy of discussion.
Where is this? See, I don't see that,
right.
Unfortunately. I can only see one line of questions at a time.
I don't know if
they're not numbered.
I don't know if you can resize your window, stretch it horizontally, but there's like a time when the question was received, and it was received at 26 minutes past 2. I mean, I can just read it out to you.
I don't have that date. See, you have all kinds of information I don't seem to have.
That's
fine.
I
can open this window? Oh, I can open this window.
Yes.
Okay. All right, so I've opened it that way. I wish I could make it bigger, but I can't seem to get more than one question. But I did at least get it horizontally bigger.
There's a little sort of horizontal bar at the bottom.
So what time? Okay, so give me a time. I can see the
1426.
time now.
1426.
1470 is, I only go up to 1103. So I
Oh,
think we're in
sorry,
different
boss.
time
Yeah,
zones.
sorry. uh, yeah, sorry. 1126, and it's Frank from Belgium.
1126.
Yeah.
Oh, okay.
So, sorry, everybody.
I only go up to 1122.
So it's
It's 1124 now here, so this would be the future.
oh right. Hang on then. Try 926. 0926. 25 past 9. Uh,
9, 7. Oh, that's
yeah.
way back.
Sorry.
Okay, I'm trying. This is actually nice software, but there's a few things that they could improve,
The human machine interface.
and this is one of them.
Yeah. 0926. Frank from Belgium. He's asked about the SIL concept. The SIL concept is technically meaningless, I think he's quoted you saying. Is that
Oh, yeah, I do. Get everyone angry with that one.
is that true for every uh, SIF, safety integrated function?
Okay, so the SIL, yeah. I debated not even mentioning it, and then I decided this would get everybody awake, um, if nothing else. Um, the SIL says that the SIL is applied to the software, right? To the component. How can you ever know about the safety of a component outside of the system in which it's operating? So this is the example of the Ariane 4 and 5, the exact same software. One worked perfectly well in the Ariane 4, but because the Ariane 5 took off at a higher trajectory, it blew up. Software ended up in an explosion of the Ariane 5 on the first flight. The problem is safety is an emergent system property. SIL is really looking at reliability, and they're looking at the component reliability, and it's assuming that component reliability is equal to system safety, and it isn't. And that's what the whole part of this first thing and why I go through all of that business about reliability and things. It's a critical assumption and a critical concept people have to make if they really want to do something about safety. Oh, Ken Hoyme. Oh, I see a name, someone I haven't seen in a long time. So the SIL, I mean, everybody means well. It's like, remember the little birds on the park feeding worms into the baby, and the baby was still crying. Everybody means well, but they're going with this old concept that safety is equal to component reliability. And as I said, a long time ago, before we were building the types of systems we're building today, that was a good simplification. It worked because we got the design errors out, system design errors. But now those system design errors are still there when we use the thing. And it doesn't matter how reliable the components are in implementing their requirements if the requirements are wrong, if the system design is flawed. Excuse me, and that's what we really have to deal with, and that's why the SIL doesn't make any sense. Now, people are 26262 in the automotive industry really comes from IEC 61508, which is where the SIL came from, and people are recognizing that, and they're just trying to add STPA into 26262. And they're adding it, they're trying to get it added into the standard so they can do something that makes a little more sense. If you want to use SIL, you're perfectly welcome to, but I do recommend that you buy a lot of insurance.
Hi Nancy, did you want to address Rick Stryker's question at 0957? Are there situations less complex where you would recommend using the old tool sets, or can STAMP be applied across all situations?
957. Oh, I've got it. Are there situations less complexly where you're recommending use? Well, certainly in less complex systems, which means probably systems without any software in them, if you have any, you can think of any today. I used to say a bicycle, but bicycles now have soft computers in them, microprocessors in them. If you have a really simple system, you can get away with the old methods, but they cost more than STPA. STPA works on all these, and they're going to be less costly. But if you want to spend more money and do the old stuff, sure, as long as it's very simple. But the problem is it has to be really simple. And what we sometimes think of as simple is not so simple after all. There are system design errors in many of these systems that appear simple to us, but we can't exhaustively test. If you can exhaustively test the system, then sure. Then you can get out all the design errors beforehand, and I'm happy. You can use anything you want. You probably don't need any hazard analysis technique for those. You just need to make all the components pretty redundant and reliable, and you don't need an analysis technique. But there's not many of those systems around today. I can't think of any. As I said, bicycles are now. People have used STAMP on fairly simple systems and found things that nobody had thought of. I think it's really interesting where after the Toyota unintended acceleration accident, the chief engineer of Toyota was quoted in the newspaper as saying, it's got to be the floor mats or something. It can't be, or operator error. It can't be our system because we have exhaustively tested our software. Oh, I hope he was just trying to make that he didn't believe this, because you don't exhaustively test, tens of thousands of lines of tens of millions of lines. You don't even exhaustively test tens of thousands of lines of software, let alone tens of millions. And engineers misunderstand this, though. They have this belief that they're exhaustively testing when I don't think they really are. Well, I know they aren't. They just don't know it.
Should we take one final question from Steve Lilly at 1506? It's about unsafe control actions. So in the STPA primer, it mentions a fifth scenario: control action required is provided but not followed.
Oh yeah, yes. I didn't. It's actually on one of the slides, but I didn't want to. It was gained so long, so much more than the 45 minutes Simon promised, that I skipped it really quickly. Absolutely. So it's not only unsafe control actions. The software could, or the human could do exactly the right thing. They could give out a safe control action and it may not be implemented correctly. And so absolutely you have to do that. And in fact, those are the things that the standard techniques find. The failures of the actuators, the failures of the components, the physical hardware components of the plane or of the device, whatever it is. And so, yeah, you do have to do that. It's just, I didn't include it because it's usually pretty straightforward, but sorry, I went over that too fast.
That's fine. Okay, well,
somebody's obviously read the primer. That's good.
Are you sort of happy now with the questions and answers? Should we call that a day and let everybody get back to their busy schedules?
What was that? I'm sorry.
Should we call that the end and give everybody, thank you for coming, and you're welcome.
Oh yeah. Yeah, thank you. Some of you have stayed. It's amazing. This has been a long time. We certainly I've been wanting to do something like this, and Simon sort of came and asked me, and I thought, oh yeah, that's wonderful, but you know, I'm actually a technological nerd when it comes to computers, and I'm really bad at all this software, so I thought, well, how am I going to do a webinar? So I think it's great. I'm really excited that Simon did this, and I'd certainly like to continue to do this kind of thing more. And you know, once we have this all recorded and people can look at this, then we can do more advanced topics, because beginners will say, okay, before you do this, you should go look at the past one, and now you're ready to go dig into the techniques. But unless you understand why you're doing such a different paradigm, it's really a paradigm change. And because of that, unless you understand the reason for the paradigm change, it doesn't make much sense when you just start in details. Oh, I forgot my paradigm change slides. I have a couple slides that I really like, that if everybody will be patient for about 2 minutes while I go get them.
Well, we could stick them in the slide pack and then send those out afterwards if you like.
No, I need to explain it, I think.
Okay.
Just a minute. I'm almost there. I just.
Okay.
Okay, here. So can you give me the screen?
Yep, stand by.
Okay. So sometimes what I do, people get scared about paradigm changes. Please close confidential. Oh, show my screen. Okay, can you see it now?
Yes. Yes, we can see
Okay.
it.
People get scared at the idea of a paradigm change. They get worried about that they won't be able to understand it, won't be able to keep up, that you know they're familiar with what they've been doing their whole life, and now you're telling them they have to change. And so I want to talk about a paradigm change, about the whole concept of it. A paradigm change doesn't mean that what you previously did is wrong and the new approach is correct. Einstein had a great quote. He wrote, "Progress in science is moving from one paradigm to another, is like climbing a mountain. The further you move up, you can see farther than on the lower parts of the mountain. The new perspective doesn't invalidate the old one, but it extends and enriches our appreciation of the valleys below." So the value of the new paradigm, in fact, often depends on the ability to accommodate the successes and empirical observations made in the old paradigm. It's not that the old ideas are wrong, but we need to get a bigger perspective, because the world has changed that we're applying these ideas on. So the new paradigms offer a broader, richer perspective for interpreting the previous answers. Isn't that nice? I like that. Anyway, that's Einstein, not me. So that's, I think, a good way to stop.
Okay.
To end, Simon?
I'll take the screen back. There we go. So I just want to say, you know, first off, thank you to you, Nancy. I really appreciate you taking the time, taking your time out to put together some slides and go through it, and particularly answer a lot of the questions. I'm sure, you know, there's a lot of people that have asked questions, and I really appreciate your response to that. But I also want to say thank you to all the attendees, because obviously without you guys, we'd have no webinar, we'd have nobody to talk to, no questions to answer or anything. If this is something that you've enjoyed, please provide some feedback. Please tell your friends and your colleagues about it. As we mentioned earlier on, we are going to run some UK-based events. The first two will be, planned will be in October. If there are any that you'd like to attend earlier than that, please go to the link on the screen, send your details, let me know, and I'll contact you and see what we can organise. And likewise with the webinars, if you'd like to be involved in some more webinars, please go to the link at the top and we'll send you some details about that. But thank you very much, and we'll see you again another time. Bye bye.